Assalamualaikum warahmatullahi wabarakatuh. See you again. So let us continue with subtopic number 3 on data connected source. So let us assume this RYB sequence and taking line voltage VRY as a reference. Then we have the following phasor expressions. So we have VRY as the reference, right? So we have another phase, which is VBR, as well as VYB, right? So and then for resistive load, so phase current are given by IRY, so 0 angle, IYB, so minus 120 degree, as well as IBR, so plus 120 degree, or this is actually equal to minus 240 degree. So what happened to voltage? So we have V line, so which is equal to V phase. Right? This means in this particular example, or this particular data connected source, there is no any differences between line voltage and phase voltage. All right. So for delta, okay. But when it comes to I, so phase current or line current, so this is actually square root 3 I phase. All right. So remember, this is applicable for star connected source. Okay. So but when it come to phase or the angle, phase angle, so we have, for example, IRY over here. So this is how we can draw the phasor diagram of the phase current. So we have over here IBR. Okay, so this is 120 degree difference, and then we have the third element which is IYB. So this is minus 120 degree. So all these are now called phase current. Alright, so this is also phase current as well as IYB. Okay, this is all phase current. Okay, now here we go. Alright, this one. So let me erase this one first. So here we go. So VRY, this is okay, the main reference with 0 angle here, and then the second phase with 100 or minus 120 degree difference, and VR 120 degree difference. Okay, so this is if for voltage. So line voltage equal phase voltage, so we have no problem with that. And then okay, data source, where source current and line current relationships. So we have the line current IR, this is IY as well IB, are related to the corresponding phase currents RY, RYB, and IBR according to Kirchhoff currents law. So basically we have this node. Alright, this is node R, for example. Alright, then this is node Y, and this is node B. Okay, so yes, this is the relation of IRY, which is leaving node R heading to node Y, and then the second one we have IYB, which is again leaving node Y and heading to node B. And then the third one we have IBR, which is again leaving IB, oh sorry, not B, and heading to not R. Okay. So according to Kirchhoff current law, we can simply say that IR is equal to IBR minus RY. So IR is stated here. So this is IR. Okay, so we do have IBR, which is current that coming to this node R. So this is IBR. Okay, so minus current which is leaving node IRY. Okay, so this is how we can relates between IBR and IRY according to IR. And then similarly for second line current, which is IY over here, IY. Okay, let me change the color. So to this one. So we have IY, so the second line current. So this is actually RY minus IYB. So we have this node Y. So we have the IRY, the current which is coming into node Y. Okay, this node, the one in purple color. So minus the current which is leaving node Y, IYB. Okay, this IY, this IYB. Alright. So then similarly for the third ones, we have IB. So IB, this is located here. So node B. So we have IYB, the current which is coming into this node, namely IYB, then minus current which is leaving B node, namely IBR. Okay, this one. So assuming a balanced RYB three-phase system with source currents defined by IRY, so this become our reference over here. Okay, RY, so with zero angle. Okay, so we could relate that IYB is actually 120 degree lag behind. Similarly for IBR. So all these are actually what do you call it? Phase current. Okay, this is actually phase current. So for IBR, this is also equal to minus 220 degree difference. Okay. If we can draw the phasor diagram, so it will look like this. So IRY, so here RRY, so with 0 degree. Okay. So we have the second entity, which is IYB. Okay, so 1 minus 120, okay, degree, so downwards because it's negative. And the third one is positive plus 120 compared to RY. So it is somewhere over here, IBR. Okay, this is another 120 degree. Plus, this is also equal to minus 240 degree if you go from here, okay, to here. So the red one is actually minus 220 degree. Okay, it's the same thing whether you choose minus 240 or plus 120 degree. So still on the same subtopic, data source, okay, source current and line current relationship. So we have again now IRI equal to RY minus RBR. So just substitute the value of IRY and also the IBR, okay, the one we have defined earlier, this one, okay, all this into this equation. Okay, So after we substitute the value, so you might get the value of IR, which is equal to square root 3 I phase angle of minus 30 degree. Therefore, so we know already that I line is actually equal to square root 3 I phase. Okay. So IR is over here. Okay. And then the line current, which is IR, here is actually minus 30 degree lag or below Ry. This means the line current IR lags 30 minus 30 degree compared to Ry. So again, the magnitude is longer. So the magnitude of IR is longer compared to Ry because IR is actually square root 3 I phase. So this is phase. Okay. So this is line. So the line current are shifted 20 degree relative to the corresponding phase current. So line current, we can conclude that line current lags phase current by 30 degree. So this is what we have drawn over here. The line current here lags phase current by 30 degree. Okay. So it located 30 degree down below. So the line current of data source as follows. Alright, so we try to conclude what we have derived earlier. So you will see that for IR, so line current of R phase is actually square root 3I phase minus 30 degree. So similarly for IY, the magnitude is same because again this is balance. Alright, the magnitude is same, equal for all three phases because it is balanced system. So again, for IY, so the initial value is minus 120. Since you convert it into line current, so you need to minus or deduct another 30 degree. So this is equal to 150 degrees. Similarly, IV, so from IVR we have minus 240. Alright, this is for phase current. So once you convert to line current, so you need to deduct another 30 degree, or you have to add up another minus 30 degree. So this is equal to minus 240 or equal to plus 120 minus 90. So this is actually, sorry, not minus 90, but minus 30. So you will simply get 90 degree for the B line current. Okay. So this is how you plot the phasor diagram for IR. So this is what we have seen earlier in the previous slide. So now come to IY. So you come to IY. So you try to plot. This is the IY. So this is actually minus 150. So it comes from here. This is minus 150. If you compare with the line, the phase current over here, this is actually 30 degree difference or 30 degree apart. Okay. And then the last one is IB. Similarly, if you have IB, okay, over here, IB, if try to plot in the phasor diagram, so it gives you actually just now 90 degree positive. So it comes from IRY, so 90 degree. So this is the place where you should write or you draw the IB. And again, if you compare to its phase current, this is actually 30 degree interval. Okay, because in the beginning. So we have seen that IBR is actually 120 degree away from IRY. So 120 minus 90, so you got 30 degree. So a good example, a balanced three-phase, right? Three-wire source applies line current of 10 ampere. Okay, so the line current equal to 10 ampere to a three-phase load. So assuming the source is delta connected, so find the source phase currents, take IR as reference and assume a RYB sequence. So we just assume this is RYB sequence where IR is the reference. Okay. So here, sorry, reference. So remember, this is symmetrical value between IR, IY, and YB because these are all, again, balance. Balance. Solution given line current equal IR equal to 10 ampere. Therefore, for a delta current source, phase current so equal to IL over square root 3. So this gives you 5.77 ampere. Remember to recall phase L equal to square root 3 I phase. Right? And then the line current lags behind their corresponding phase current by 30 degrees. So when IR is defined as the reference phasor, the phasor source currents are. So this is once you convert into phase current. Okay, because the line current, so line current lags by 30 degree. 30 degree compared to I phase. Okay, that means once you want to convert into I phase, you want to calculate I phase, so it is the other way around. That means IP is now equal to minus 30 degree if you convert from IL. Okay, just like this one. So the line current is actually your reference here. Okay, just now in the previous slide, so IR is the line current which become your reference. Okay, but you want to convert this IR or line current into phase current. So according to this relationship, so phase current IL to phase you add plus 30 degree, but from phase current to line, from line to phase, so you need to deduct 100 and you need to deduct 30 degree. You have to plus 30 degree, just like this one. Okay, just like this one. So plus 30 degree. So the magnitude or RMS value 5.77. So plus 30 degree. So you will get 5.77 30 degree ampere. So similarly for second phase current RIYB. So similar magnitude. So this one is minus 120 degree plus 30 degree. So you get minus 90. So the third one, IBR. So we do have same magnitude over here, current magnitude. Okay, and then you have plus 120 plus another 30 degree. So you simply get 5.77, 150 degree ampere. So this is how you should plot your phasor diagram. Okay. This is how you should draw you should draw or you should plot your phasor diagram. So IRY, so it is now lead IR by 30 degree. Okay, similarly for IYB, so it leads IY by another 30 degree. So similarly for IBR, so this is another 30 degree. Okay, so you may also plot directly from this angle value where IRY is 30 degree here above above IR. Okay, so IYB is minus 90 degree, is minus 90 degree here. Okay, from IR. Okay, from IR to IYB, so this is minus 90 degree. And then similarly for the third one, IBR, so we have 150 degree from IR, so from IR up to IBR over here. Okay, this is 150 degree. Where later on you will notice that the phase current IR, IYB, RBR all in red is actually like 30 degree behind the line current here and here. So subchapter number 4, data to Y transformation at source. Okay, converting a data connected source into a Y connected source, assuming a RYB sequence again, and taking phase voltage VRY as reference, then we have the following phasor expressions. Okay, where V is the RMS value of the line voltage. VRY, so become the reference over here. Okay, and then we have BYB, so negative 120 is for this phase, as well as the third phase, which is BBR. Okay, for this one. Okay. Now we try to convert it into star. Okay, similarly we have VRY, VYB, and BBR. So inspection of phasor diagram gives us the following expression. So VRN equal to V, this is actually V line. Okay, all these are actually V line, so these are all V line. Okay. So according to what we have learned earlier, if you have the star connected or star configuration, okay, so once you convert to phase value, either VRN, VYN, or VBN, so you will see that the magnitude, the angle is actually lag behind by 30 degree. Okay, this is for BRY, for example. Okay, this is BRN. Okay, so similarly for the second phase, BYN and BBN. So all of them you just deduct by 30 degree. Okay, this one. So we have VRY over here. Okay, this is for line voltage. So this is the phase voltage. So phase voltage is lag behind by 30 degree. So this is similar. This is actually similar to what I have shown over here. This one. Okay, don't get confused. So VRY, and then this VRN. So if you go to second phase for VI1, YN, so you will see the same situation. So you have over here YN and VBN. This is actually another 30-degree difference, or you can actually directly plot from 140 from VRN. From VRN, so up here. Oh, sorry, no, from here. Okay, from VRY. So this is actually the purple color is actually 100 minus 130, 150. Sorry. And similarly for VN over here. Okay, so you may plot according to the phase angle value 90 degree from VRY. Okay, VRY. So you have 90 degree. This is VBN. Okay, this means all the phase value you are plotting according to line reference VRY. So this is the reference. So unfortunately, the reference is not a straight vertical line. So you may get confused from that. Okay. So three-phase load connection. Right? So we have seen the source connection of the three-phase system, the balanced three-phase system. So what about the three-phase load connection of the same balanced three-phase system? So first, current relation for a balanced star connected loads. I believe a balanced load is one whose phase impedance are equal for all three phases. Similarly, just like the sources, we have the same value of V, for example, but now when we come to load, so the impedance, the Z value is equal. They are all equal for all three phases. So we have Z R over here, so we have ZY over here, as well as the third phase, which is ZB. Okay. Assuming a balanced RYB source and defining the phase voltage VRN as reference, we can write for line to neutral voltages VRN. So again, the reference, so VYN, so the second phase, and I believe you are very much familiar with this relationship, and we try to consider the phase load impedance B, okay, ZRN equal to ZYN, ZBN, where this is actually equal to Z, and this is the value, okay, the magnitude of Z with its theta angle. Now then the phase load currents are, so according to Ohm's law, we have V equal to IR. Alright. So rearrange the equation, you might get this expression where I R bar equal to V over Z. V is the reference. Again, go back to here. Take all this value, these three value, okay, into this equation. Alright. So substitute the value, and then ZRN is given above. This one. And then we get that the value, or the answer for IR is actually V over Z with negative theta. Okay. And then when you come to the second equation, so IY, so just take value of VYN, okay, over ZYN. Remember ZRN, ZYN, ZBN, they are all equal. So V equal minus 120 degree over Z theta. So solve this equation, you will get minus 120 minus theta. Alright. So now you can see the trend. So from theta, the origin, the reference, now the value for second phase IY, it is actually 120 degree lag behind IRY. Okay. So this is 120 degree lag behind. And then the third phase, which is the B phase, again, take VBN over ZBN. So this now we have minus 20, minus 240. So we have minus 240 minus 10. Okay, so this is lagging behind IR by minus 220 degrees. Okay, so this result shows that in balanced YY three-phase system, the phase load currents are balanced, meaning equal magnitudes, phase angles at 120 degree interval. Okay, so from IR, okay, same magnitude means the same length of arrow, the one I am drawing right now. So same length of arrow. So we have the second phasor, which is IY. Okay, same length actually here, the one I am highlighting, and then the third one is I. Okay, this direction, this is IB. All right. So same magnitude means same length, and then with equal phase angle of 120 degree interval. This is 120 degree, another 130 degree, and then this one also 120 degree difference. Okay, so thus the phasor line colors may be written in general form as IR, okay, IL minus 10 minus theta, sorry, IY minus theta minus another 120 degree. So IB, so this is actually minus 240 or equal to plus 120 degree, where L is the RMS root mean square line current. Okay, so this is VRN, this is VYN, VRN, VYN, and then the third one is VBN. Now we try to draw uh, the phase current, which is IRN, okay, theta, and then YRN, YN, as well as IBN, okay, theta. Okay. So the line current magnitudes are equal in each line current lags the respective line to neutral voltage by the impedance phase angle theta. So it means that the line current over here, so lag by the same value of theta here, this one, minus theta, minus theta, minus theta. This is from its VRN. Okay, this is from VYN. This is from VBN. Okay, the minus theta actually lag behind this value. Okay, so for example, IR1 is lagging behind VRN, IRN, sorry, lags behind VRN by negative theta. Similarly, VYN is lagging behind IYN is lagging behind VYN by negative theta. So IBN is lagging behind VBN by another negative theta. Here, this negative theta. Okay. So notes RI. Okay. So IR, IY, IB form a balanced set of phases of equal magnitude and at 100 degree spacing or interval, since the angle of theta is same for each. Okay. So try to come up with a balanced set of phases. Okay. Equal magnitude, and then they are actually 120 degree interval between one to another. So resultant must be 0. Okay, all the total RY plus IB plus IY, this is equal to 0. So the condition of balanced currents can only exist for equal impedance in the load. So IR, IY, IB, so they are only balanced with the balanced impedance ZB, ZR, ZY. Okay. So the current in each phase is the same current in the line supplying it, so that the line currents are equal to the phase current. So this is IL equal to IP. Okay, as simple as that. So we can make the assumption with a balanced load that what is happening in each phase does not affect what is happening in any other phase between these three R, Y, and B. Okay, it doesn't give any effect from one phase to another. Okay, so we can also say that whatever happens in phase R will occur in a Y phase 120-degree later. Okay, later, and again in phase B 240-degree later, assuming a positive phase sequence RYB. All right. So it will not happen in the same time or in the same phase angle, but later by 120-degree interval. Okay, thank you very much. See you in my next video for an explanation, a bit, what do you call it, example for a better explanation.